Okay, welcome to another wonderful week at the Complex Systems Workshop. Our speaker today is Riolo, who is going to be talking on host-parasitoid dynamics in a spatially heterogeneous environment. It's an agent-based model.
Well, actually, right now we're working with a numerical model, but we'll get into that a little bit more.
Cool.
You admitted this is a canned talk, right? That you already gave it today?
No, this is a different one.
No.
You get it. Yeah. You get a different
She had
talk.
to talk before my class today.
Right, so I'm going to talk a little bit about these host-parasitoid systems in general before we get into the particular work that I've been doing with Honey and Mark Hunter lately. So what gets classified as a parasitoid can be a little bit fuzzy, just like what gets classified as a predator versus a parasite can get a little bit fuzzy. But in general, the life history that we're thinking of when we think of a parasitoid is that we've got the juvenile parasitoid is living inside a single host organism, and in the process of maturation, it usually kills the host or sterilizes the host. And then the free-living adult stage will go and find some other host organism to oviposit in and start the new juveniles off in their obligate parasite stage. So you see a lot of this kind of system among insects. The number that I've heard tossed around is something like 10% of insect species being parasitoids, which pretty amazing, but also that a whole lot of insects also have parasitoids, at least among their natural enemies. So there are a lot of different systems. One thing that we see a lot are parasitoid wasps. So this is a picture of a parasitoid wasp in the process of ovipositing in this aphid here. If you see these guys flying around, you can usually notice them by having kind of a pretty long, noticeable ovipositor. So that might be, you might have seen those flying around just out in the wild. The kind of really traditional model, mathematical model of host and parasitoid population dynamics is this pretty old model called the Nicholson-Bailey model, where there are a lot of variations on the theme, but the kind of maybe most well-studied version is that the fraction of hosts in the population that escape being attacked by parasitoids goes down exponentially with the parasitoid population, right? So your chance of, if you're a host, your chance that you get to reproduce is decreasing exponentially with what population of parasitoids is right now. And the reason that this model is kind of used a lot is that it captures one of the big features of host and parasitoid population dynamics. If you've got a well-mixed population, right? If everyone's encountering everyone else, what you see is that you get this unstable situation. You get a big boom in the host population, they get built up, and then the parasitoids population skyrockets, and everything busts. Everybody crashes to extinction. There's so that's sort of a nice mathematical property of this system that we do see in real life. You can see experimentally that if you keep a very local population of any kind of host and parasitoid system, that you will see little fluctuations, big boom, big bust.
Maria, do you know, did they originally do this in terms of differential equations or difference equations?
I think actually this is almost always done as difference equations, and the reason is because the most studied version of these systems are in insects, where both maybe the host is like an herbivorous insect like aphids, and the parasitoid is something like wasps or those. And the thing about insects is that they have these very structured life histories.
Yeah.
So in some sense, the difference equation is actually more reasonable because you get these because synchronized generation times is what you actually would expect to see in that system.
So the only equilibrium is 0, or is
there's another unstable equilibrium. That's and you can kind of see these oscillations are around. Let's see, we can figure out what it is. It's usually quite low compared to the size of the peak populations. Once you actually get a little nudge off that equilibrium and get the big boom bust going on. So one thing about this Nicholson-Bailey model, right, is that that previous case we were looking at is everybody's meeting everyone else. It's a very local, well-mixed population. If you allow a bigger space, right, where hosts on one side aren't coming in contact with parasitoids on the far on the other side. In other words, if we just have local mixing of a population in some big space, then we get slightly different effects. The way that I've mostly seen this done, and the way that we've been doing it so far in our research, is to basically throw the whole thing on a lattice, right? And there's some range that hosts and parasitoids can get to, can disperse to, and there's some rate at which they stay versus disperse. So far, just to keep things simple, we've mostly been looking at the case of dispersing to your 8 neighbors in a lattice. One thing that's, well, we'll get to that a little bit later, about different effects that might have. So when you allow just the local dispersal, so that, and if you have a big enough habitat, something interesting will happen as soon as we get somewhere that has video. Let's see. Didn't want to play anything, so let's start it up right here. This is what we're going to see is how the population density of aphids changes over time. So we start out just with noise.
What do the colors mean?
Oh yes. Blue is low population, and as we get to warmer colors up to red, we have higher population densities. Just so that we can see the difference between near zero and zero populations, we've got actual zero colored in black and near zero colored in blue. So if we watch what happens over time,
Are you sure that's not the local weather forecast?
So there are actually quite a few systems that do things like this. These kinds of spiral waves coming out. Apparently, I only just recently heard about this, but you also see that in heart tissue. Sometimes after a heart attack, you'll get spiral waves forming, and that can actually be something that we see. But those are pretty characteristic of what we see in a Nicholson-Bailey model with local dispersal. You get these spirals that that will form, and then you'll see that for as long as you care to run it. In the and it does depend on the regions of parameters, but in general, things that you see if you've got a big space and local dispersal that you don't see in the quick little boom and bust extinction of local places are that total populations, if you counted up over the whole space, if you summed up all the population densities, get pretty stabilized, right? It takes a little while when we start with this noise state for them to get into some kind of quasi steady state where they're just they're oscillating around a little bit, and you see some bigger and smaller peaks, but in general, they seem pretty stable. There also seems to maybe be a little bit of some kind of periodic thing going on here, right? But not quite periodic, not like some kind of harmonic oscillator, but there's a little bit of a sense that these, it doesn't look like, it doesn't just look like noise. And that's, if we look at what the local populations are doing, it looks even more periodic. So we get these local booms and busts still, which you can imagine when we saw the spirals going around in the video, each of these local peaks later on is an arm of the spiral like moving across this patch, right? So it's like one of these moving fronts of aphids. And if we see they're just a little bit ahead of the, actually in this case they're just a little bit, can't tell if they're a little bit ahead or a little bit behind you. But when you watch these, you can see the wasp fronts are kind of chasing the aphid fronts in essence. So if you have a big enough space, there's sort of room to escape and room to get this swirling around motion going on.
I missed one detail, Maria. Is the rate of migration proportional to the density at the locale?
Ah, good point. So the way that we're having dispersal happen right now is aphids just aphids have a fixed probability of staying where they are and a fixed probability of dispersing kind of uniformly among the 8 patches around them. But with the wasps, we're doing something a little bit different here, which is that that wasps are tending to aggregate to where there are more aphids. And this is something that you can tune. And I think that even without much of this aggregation, you can get this happening. But basically, the way we do it is the probability that an aphid migrates to patch I is going to be aphids at patch I over the total aphids in range raised to some parameter mu. So if this goes to 0, then you've got uniform dispersal of wasps. As this goes to infinity, everybody just piles on the best-looking aphid patch right next to them. And if you have 1, the wasps are going perfectly proportional to the aphid population. We've got it set at 1.1, which kind of gives just a little bit of extra favor to the more heavily populated patches. And the reason is just because this is something that we tend to see in the wild, so it's definitely something to play with in the future. But for sort of a base setting, right now we've got that set at 1.1, so slightly more than proportionally wasps will disperse to aphidier patches. So in addition to these local booms and busts and more or less stable metapopulation dynamics, we also get these characteristic spatial structures, right? These spiral waves that form and will sometimes drift around, and aside from being really pretty, are pretty persistent and pretty interesting. So one question is, how robust are some of these features, right? Because right now, what we're looking at is, in these past slides, is a perfectly homogeneous environment, right? Where no matter where you are, the aphid fecundity is the same. So the hosts are going to do just as well over here as they are over here. And there's no variation whatsoever. So what happens if maybe some of this habitat is higher quality than others, right? You might have really great plants over here, and over here maybe it's not so great, but then over here maybe we've got some more good stuff. So how is that gonna change these dynamics? Are we still gonna see these internal dynamics driving us towards something that looks like this, or are we gonna see the environment really determining what comes out here? So just to start with kind of a relatively simple extreme case, we've been so far kind of experimenting a little bit with basically just having good patches and bad patches. In the bad patches, you don't get to reproduce if you're a host. The good patches, you get to have 2 offspring if you're a host. And within this framework, we're going to play around a little bit with what fraction of patches are habitable, right? So Is it almost all good? Is it almost all bad stuff? And also, how are the patches correlated with their neighbors, right? So what's kind of the characteristic size of patches, and especially in a lot of if you've got an herbivorous host, herbivorous insect host, you can imagine that a lot of plants do have kind of a typical spatial scale that you'll see similar plants in. So that could also make a difference to the dynamics of this system. So just to kind of look at a couple example runs to get a feeling for the kind of stuff we're seeing and get a flavor for what's going on here. So these are a bunch of environments generated with the same random seeds. So they start with the same noise, and then we can either let different percents of them be habitable or not, or have the kind of smooth them out more or not, have them be more correlated or not. So you can see that as we go from 5% to 50% to 95% habitable, you can imagine that the dynamics here are going to be pretty different than what we've got over here. And also that as we get bigger clumps of similar patches, that's also going to influence what goes on. So the most sort of basic question we can ask is, are we still stable? Do we get persistence? And so just in these sample runs, we only ran for 1,000 generations just for the samples in this top. I've got some longer ones cooking on the CSCS cluster machines. But just to look at these guys, we can see that by 1,000 time steps, in the 5% habitable case, we're already seeing a kind of interesting trend here. So when we had uncorrelated habitat, when we had this noise, we're actually getting pretty good persistence. And one idea that we might be thinking about here is that this is almost like a system of islands, that can have reinvasion events and can get between each other. Another thing to note is that we're measuring persistence as in how long the wasps last. Because if the wasps go extinct before the aphids are just going to keep going to infinity. We don't have any kind of density dependence or anything like that right now built in. We're just seeing, can we sustain both aphids and wasps? Yeah.
Just a question about dispersion. On the top one, it looks like there are almost no neighboring useful patches. So how do the aphids get from patch to patch?
Excellent point. So there's an interesting thing here. So because there are almost no neighboring patches, the aphids can't really get between these different little islands. But what can happen is that we can get wasp populations moving around a little bit. Because even though, so say we've got two habitable patches that have two inhospitable patches in between them, right? So aphids get to reproduce here and aphids get to reproduce here. And let's say that we start out that over here there's some aphids and some wasps, and over here we've got some aphids but no wasps. Now what's going to happen is that when the aphids disperse, we'll get some aphids spilling out into the surrounding 8 neighbors of these patches, right? And these aphids in here, they're pretty much doomed, right? A few aphids are kind of wandering off into the void every generation, and they're not going to make it. But we can also think about, well, when we have some of our wasps dispersing into these patches, they can still use these aphids that, even though they can still oviposit in these kind of doomed aphids, and the juvenile wasps will do just fine, and then have another chance to disperse here and to disperse here. So in some way, the patches that are habitable for wasps are there's sort of a little corona around the habitable aphid patches. And at first I thought this was kind of weird, but it turns out that this is something that we actually see a little bit in nature. Chatting with Mark Hunter, he mentioned that there are some species of aphids that will kind of disperse too far north out of their range, for example, like up into Michigan, and they're not going to be able to overwinter up there. But some of their natural enemies that follow them up will do just fine. So we kind of get a supplemented parasitoid population because of these aphids that are bringing them along.
It's a sourcing data.
Yeah, exactly.
So in a sense, it might be better for the wasps to have the uncorrelated than the correlated, because the correlated creates bigger white spaces that might be harder to breach.
Yeah, exactly. So, right, down here we've got bigger islands, but it might not be really big enough to keep going on that island. But at the same time, you've got these impenetrable gaps between them. So right, even by the time we get up to radius 2 patches, it's sort of, they're not going to last long in this guy. We're going to have a pretty quick boom and bust of wasp population, but there's nowhere to go from there because the good stuff is too far apart.
Can you talk about how you're actually constructing those landscapes?
Sure. So the way that we're doing it is we start with just random noise, and these are actually all generated from the same noise seed, and then running over basically convoluting you have a big array of your noisy values that you generate between -1 and 1. And then you're convoluting with some kind of matrix of, and this is just kind of, there are probably a lot of other ways to do this, but this works pretty well, of just everybody within a certain radius is going to get a little extra boost from, to be correlated like this, right? So we're convoluting a matrix of zeros outside of this radius of ones inside. So in the correlated in radius 2 case, we're just saying we've got a little 5x5 square of, listen, not quite 5x5, because we're trying to make it round instead of square, but we've got a little circle of radius 2 of all ones, and we're basically just running it over this thing as a smoothing, as a way of smoothing it out. And it seems to generally kind of work. There may be actually better ways out there, but this is just kind of a quick and cheap way to get a little bit of correlation with it. And then we can do a cutoff of what percentile is going to be the good stuff versus the bad stuff. So right, so just like Jim predicted, when we get a little bit of correlation in the 5% habitable case, it's a disaster for the wasp. And in particular, there's this sort of interesting trend, right, where in the radius 2 case, where we've got these really tiny little islands of good stuff that are isolated, it goes off really fast. They're done for pretty quickly. Whereas there's a little bit longer time of persistence when you have these slightly bigger islands, and that is probably because, in general, as you get a bigger habitat to work with, there's sort of a little bit more time before things really crash. You can sort of, there's a little while of sort of a miniature version of the big dynamics with the hosts escaping their parasitoids and moving around. But there's not quite enough space to keep it going. Yeah.
And so is this? Okay, no, never mind. Is this the same area, even if it's correlated? Are you sure about that?
Like with
Yeah.
Yeah.
How big are those? Just out of curiosity. Are they 50/50?
Yeah, these are 50 by 50. And yeah, it does make a difference how big they are, because you can, if you have a really big environment, you can also by chance kind of you just happen to get a big island. So one thing that I'm thinking about doing in the future is looking at something like, after we generate this, let's run it through, a Fourier transform or something to see what actual spatial scales we're getting, to make sure that we don't just think we have typical size scales.
So the
Yeah.
population size is linear or at least proportional to the size of Aaron? Of the host population? At the initial?
Yeah. Let's see. So the way that we're doing initial population is that at each patch we're perturbed from the equilibrium. Right. So in these cases, what we would start off is nothing in the bad stuff, and at each patch of good habitat, we'd have some slightly perturbed from equilibrium value. So the total population on a bigger island would be bigger. Yes. Yeah. Let's see. The next, another thing we were kind of looking at was before we saw this kind of quasi-periodic behavior in the local populations. I thought it might be neat to take a look at, if we count up at each patch, the time between peaks of local populations. And so if we just toss everything in a histogram, one thing that we can notice pretty quickly is that there's kind of there's a difference between how widely spread these things are. Once we get up to a lot of good habitat, we get very tight peaks in time between peak values and local populations. So one thing that kind of suggests is that there's either something more periodic going on here, or at least that everything in the whole habitat is kind of operating on a similar time scale.
Excuse me, what are the plots there?
Yeah, these are all tiny. Sorry, these are just a histogram of each time we saw at each patch. We counted the time between each pair of peaks in local populations, and I think this was just for the aphids. So this was
Each subsequent pair.
each subsequent pair. Yes, thank you. Yeah. So from this peak to the next peak to the next peak, in each of the 2,500 patches.
Maybe you want to use some sort of wavelet ones?
Yeah, I think that might be a good idea. We haven't tried it yet, but I think that's probably a really good idea. And just to kind of see what the trend is, because you can't see the scale on those next pods, it does seem like there's definitely some signal going on. These are the differences in mean time between peaks are a lot bigger than the variation within one run of mean time within peaks. So I think it's definitely something worth looking into farther. This is kind of all, this stuff is a little bit hot off the press from this week, so we haven't had too much time to play with it. But there does definitely seem to be something pretty interesting going on. Especially in that, I was a little bit surprised that we've got faster, well, not entirely. So we seem to have these much faster peak-to-peak times in the 95% good habitat versus these other ones. And one possible reason for that is that these peak-to-peak times might be saying something about sort of the characteristic distance between patches, right? So you could imagine that the path that you have to take for a front to get from here to here might be pretty wiggly and have to go through some weird twists and turns, whereas from here to here, there are some little holes, but you can just divert yourself a little bit and pretty much get right on by. So I don't know if that's what's going on, but that's one possibility. Oh, yeah.
How do those percent habitables relate to do they relate to the world? Because I imagine you chose them because they're easy, but you know, like it looks like 50 and 95 aren't that different, but the 5 is much different.
Yeah, and I think I think that's probably true. We need to get kind of a more fine-grained look at these, but one reason that the 5 might be so different than the other two is just what we were looking at before, where the connectivity for aphids, if you wanted to have, for wasps, if you've got wasps and aphids here, in order to be really isolated, you have to have in these 24 neighbors no aphid patches. So that might be why down at 5% we're seeing something very different from higher up, in that the typical level of isolation is probably pretty different. And there might be something pretty sharp going on. I've been kind of wondering if there might be some kind of percolation transition if we look really closely.
So I was, it would be like an S curve where you hit this point.
Yeah.
Might be a straight up phase transition.
Right, it could be. Because you can imagine a lot like with, anytime you're looking at connections in a network, there's going to be often some point where you have a chance of getting a giant connected piece, right, where in some sense you're spanning the whole thing.
Maria, are you familiar with a lot of this new literature on regime change and detecting it? Because
a little bit.
so there's this idea that when you're on the cusp of some big qualitative change in the system, there will be these signals, one of which is called critical slowing down.
Mm-hmm.
And basically what it ends up giving you is more temporal autocorrelation.
Okay.
Which seems like that's kind of what you're getting on the left-hand side. So you may be kind of detecting that you're on the cusp of a collapse or a regime change.
Yeah, that's a really good idea. I hadn't even made that association, but that's a great idea that this could be that could be what this signal is. What's going on? Okay. Right. So that could be why we have this dramatically slow place. Is that we would expect 5%, even just thinking in the most simplistic terms, thinking the probability of a particular patch being isolated versus not isolated, at least in the uncorrelated case, would be 1 in 24, right? So even in the most, like, we're not doing anything complicated at all case, the average patch transitioning from being isolated to not isolated is pretty close to around 5%. So we might be right in the middle of kind of the interesting phase transition going on here. Yeah.
This is a really kind of micro level question. Have you tried a system where you have exactly 2 patches separated by exactly 1 or 2 spaces?
I haven't done exactly 2 patches by 1 or 2 spaces. What I have done is a big environment with sort of fire breaks in it, essentially. So we'd have a line or line or 2 or 3 of bad patches, and then somewhere else, and doing that, and starting with different combinations of where there started out being aphids versus wasps.
I'm just wondering, it doesn't seem likely, but it's possible that if you have a system where you just have 2 patches and wasps are diffusing back and forth through the sort of boost connection that you talked about, that would actually be self-sustaining, just those 2.
That's definitely worth a look. I haven't tried it, but I think it's possible that we could see something like that happen at least in some regions of parameters. It seems like there's a little bit of a question of, in essence, recovery time for the one patch as the wasp population moves over. And also, it seems like aggregation would be a big thing that would matter. So if you had really high aggregation, you can imagine that once this patch gets depleted, suddenly the neighboring area starts looking pretty good, and a lot of the wasps go over and let this patch recover a little bit before they come back. So I can imagine that if you had strong aggregation, you could see something like that, and that's definitely worth looking into.
Yeah, I think in metapopulation theory, when you have basically 0 and 1 state, you can, if you have 2 patches and they're synchronized, the global persistence is going to go up, just by chance.
Yeah, that's definitely something that we should look into, is sort of in see if the metapopulation dynamic literature has done some similar stuff to this. But it seems like, especially for the kind of mostly far apart patches, like in the uncorrelated 5% case especially, it really does kind of look like a system of islands with rare dispersal events between them. And then, of course, the other question is, even if we get persistence in some of these very different regimes, does it look the same? Are we doing similar kinds of spatial pattern? So, one thing is, these are actually all videos, and I don't know if we're gonna. Whoa, that's different. Anybody know what to do about that? So we've got a lot of different. So we probably don't want to watch all of these, but just to pick up. Oh, come on.
Just click.
Just click? Really? That's not true. Oh, there we go. Okay, there we go. It wants that arrow. Okay, here we go. So if we look, say, at, let's take a look at this, one of the 95s. Which level of clustering do you guys want to see? 4? 4? Let's take a look at 4. So we can see a couple big holes. So let's keep our eye on this guy here and see what's happening in the region of these heterogeneities. If we let this doesn't seem to be something's wrong here. Well, no. Okay. Well, okay, so the video doesn't seem to want to play, but we can at least get a hint, even from looking at the still frames, that in all of these 95% habitable cases, these are all snapshots from, I think, 200 steps into the run, that we can see that we still do kind of settle down to something that looks an awful lot like we've got some spirals. One thing that I've heard suggested that we really ought to look into is that some of these heterogeneities might tend to anchor. The spirals might end up getting anchored to these little heterogeneities, and apparently that's what we see in generating spiral waves in heart tissue after a heart attack. Will be you've got a little area of dead tissue, and if it's in kind of the right size range, it'll kind of become the focal point of these spiral waves. And so I don't know if that's something that happens. We haven't looked at that much yet, but it's definitely something we should look into. Another question is, at this 50% habitable state, where we've got pretty good persistence when we were looking before. Let's see if we can get this view back. So in all of the 50% habitable cases, we did get persistence, and we got slower, but not as incredibly slow as the 5% case, peaks in local population. So one question about this might be, is what we're seeing, oops, so unfortunately the videos don't seem to be cooperating right now, but maybe they will, maybe we can try after. But what we do see is we definitely see movement in these high population peaks, right? So they're definitely moving around, but there's kind of a question as to what we're seeing. Are we seeing something like this? Are we seeing spirals in this two-dimensional world, but some of them are turned off, basically, right? Are we seeing kind of the same shape of motion, but some of it's just flattened out because we've got this uninhabitable area? Or are we seeing something that's very different? Like we could imagine on this thing here that we might almost be seeing something more like a one-dimensional movement of these fronts, right? So we could imagine that at least in some of these configurations where we've got a big enough cluster to sustain coexistence, but that the cluster is sort of thin in some sense, right? Where what we've really got is kind of a weird crinkly tube And the wasp and aphid can't really get from here to here without going through a long progress around here and over back. So is something really different going on in these sort of in-between values of habitable environment? Yeah.
In the 95% case or the 100% case, is there any characterize the way the spirals as a whole move? Like characterize how the center moves around? Or anything?
Let's see. I don't know. I imagine that somebody does, and I should look into it more. We do see they definitely drift around a little. So if we look at back at that video of the 100% case, wherever. Okay, never mind. Okay. Okay, I give up on the technology. But when we look back at, if we did look back at that video, we would see a little bit of, they do sort of drift around. I'm not really sure how this motion is characterized, right? If there's sort of a characteristic speed of the center relative to speed of the arms. Does the direction of rotation change which way they kind of proceed? I don't know. Those are all really good things to look into, though.
I know there is one method from Ottar Bjørnstad to estimate wave direction and significance based on time series data.
Oh, cool. What was that?
I've probably got the paper.
Oh, great. Thanks. That would be really useful to look at.
But I don't know if it can tell you something. It will maybe can tell you that it's not significant rather than something else.
Yeah, and it might at least help us detect if there's any differences between how the spirals move in the 100% case versus the near 100% case or something like that. Yeah. So anyways, a couple of the things that we're hoping to look into as time goes on are, is this really a percolation transition kind of thing? Is there this kind of sharp phase transition as we increase the amount of habitable land or increase the correlation, or who knows? Is this a sharp thing rather than something that varies more slowly? When we do get persistence, right, comparing, say, the 50% and the 95% cases, do we have similar or spatial patterns showing up, or is something completely different going on? I don't know. What's going on with this time and peaks between local populations, like you mentioned? Is this a signal of being near the phase transition, this big slowdown, or is something else going on? I don't know. There are a lot of kind of questions right now because this is still pretty preliminary research. Other things that we're hoping to someday look into are the effects of dispersal distances, right? So one way you can imagine looking into how much to connectivity and percent of good habitat are affecting what's going on would be to use the same environment but say, okay, another way to increase the connectivity without changing the environment at all would be to let the aphids and wasps disperse a little farther, right? So suddenly maybe these islands aren't so isolated anymore. And so without changing the environment, we could have a comparison of if we change that connectivity. The thing to keep in mind, of course, is that if dispersal distances get really big, then we're kind of almost back to this well-mixed population. So it'll be interesting to explore there how the dynamics change as we change the dispersal distances, both in absolute terms and also relatively, right? What if aphids have a little bit longer dispersal rates than wasps, or vice versa? Under what conditions do we still get persistent? We seem to be having a little bit of lag here on the computer, but But the other things that we were interested in looking at are how much does it matter that we're using this deterministic numerical model with the continuously varying populations? Are we getting kind of an addo-wasp situation? For those of you who remember the addo foxes, the famous rabies spread model, where you're getting a giant change in dynamics because of these itty-bitty, like 10 to the negative 28th wasps dispersing across some gap and then getting established. And so would we see something really drastically different if we had a discrete stochastic model? And I don't know, we might. Definitely worth looking into. Another thing is, and this is much more down the road, but that might be pretty cool, is, of course, when you have these big buildups in host populations, it's not, A, you might get density-dependent effects, but B, especially if we're thinking about a system where we've got some herbivorous insects as our host population, the density, their population density is going to affect the quality of resources in the future that the next generation gets to have, right? So this is something you see a lot, where is that you can already see a kind of a boom and bust system going on just with the insect herbivores on their own get overwhelming the local plant population. And so one question would be if we've got a different time scale of variation in local habitat quality going on, and at the same time as we've got these host and parasitoid dynamics happening, what are we going to see? But that's probably for quite a bit down the road. Anyways, that's it. Any questions? Yeah.
Could you pick up generations to extinction target?
Yeah.
Yeah. So I'm curious. So that's just generations to extinction, but I'm curious that if you put the sort of fraction of population versus the sort of equilibrium population, what you would see in those various cells.
Yeah.
Because I'm sort of wondering, and maybe we'd have seen it if we'd seen the movies, the whole grid and stuff like that. I'm sort of wondering, like in the 5% habitable case, if what you're ending up with is one island that is sort of pulsing, but all the rest of them are sort of all had died off or something like that.
Yeah, I think sometimes. Let's see. Let's try it one more time with these movies, because we do see sort of this gradual die-off of islands in some of the cases, especially, but let's, come on, let's see what we got here.
Claims it's running, it's not playing.
Yeah, it thinks it's playing, but it's not actually changing. Okay, so much for that. But certainly in like the 2, 4, and 6 cases, what we do see is that basically the islands kind of turn off one by one. And whereas something very different does seem to be going on in the 0 case, though, because we do see a little bit more movement. We see a little bit more, ups and downs. So it does seem like there might be some kind of metapopulation dynamic-like thing going on there when there's sort of a big enough system of connected islands.
If this was a predator-prey case, the behavior will be the same. The rules are like similar.
Let's see. I guess it probably depends a little bit on which model you use, but I think people have done some similar things with predator-prey. I don't know as much about that. I know that one thing that people have done before, it's not quite like that, but it's a little bit similar, is had a Prisoner's Dilemma game on a lattice, which also does generate interesting spatial patterns, although different ones from this. And so, yeah, I'm not sure what predator-prey does when you put it in space like this.
Well, I asked because the time series is very similar to the other.
Yeah, so it might have something similar go on. It might also depend on what region of parameter space you're in, because one of the things about this is that the reason that you always get the local crashes, and so that's what kind of makes the spiral arms of this thing show up, is that it's locally unstable. So if you were in a region of parameter space where predator-prey dynamics would have a stable coexistence equilibrium, you might get something really different than if you had something where where you'd expect to find a limit cycle, or where you'd expect to see everyone goes to extinction, or something like that. So yeah, I don't really know that much about that.
Maria, have you run this, I mean, just once to see what happens if you run it for 10,000 or 20,000 to see whether it eventually dies out regardless?
Let's see, I haven't, and I probably should. I think other people have, but I can't think off the top of my head. But yeah, that's worth looking into to see if, especially in some of these cases where, like, say the 50%, to see if way down the road it's going to crash, even if someone has studied the homogeneous.
Yeah. If you get some kind of expected lifetime, that would be good.
So I'm curious about the system. And is there any data on like spatial data on this system that you can look at?
I think there were some. Yeah, I think there were some famous experiments a while back of. I forget who did this, but someone set up a bunch of oranges, basically, as a habitat for their host species, and had the parasitoid and the host in this sort of lattice of oranges, and the distances between these would kind of determine whether or not you got persistence. And the general thing that I think they were seeing was if dispersal between the oranges between different oranges was possible, then you could get persistence. But if you spaced them out far enough that they were isolated, each one would crash in population.
I'm just thinking along similar lines. Is there any reason to believe that, like, outside in the real world, you actually get these Paisley spiral patterns, or is that something that comes up sort of in the edge case that the model produces, but not in the real world?
So I really don't know about that. That's kind of one of the things we're trying to get at a little bit, is sort of how far from this idealized system do you have to get before you stop getting this kind of particular dynamics. And I don't know if there's been any, that would be really cool, I should look into that, if there have been any like big field studies of, doing a survey and seeing spiral wave propagating or anything like that. I think you probably do see fronts moving around, but I don't know if you get that Paisley look or not.
I know you get fronts. I've seen fronts in rabies studies, fronts. I don't know about spirals.
So like ash borers, or
What?
like ash borers eating trees.
Yeah, or like those moths or some of those things. Yeah, I don't know. That's definitely worth looking into to see if there's any kind of large-scale data. One thing is that it might actually be pretty, depending on how big these scales are, it might be pretty hard to tell the difference between just a moving front and being the arm of a spiral, especially if you've got, if you do have this kind of heterogeneous habitat where you've got interruptions and things. It makes it maybe trickier to measure, is this really a spiral, or is this two fronts, or is this something totally different?
Something that would tell you a little bit about that is, if you look at the spiral, does it disappear from the inside out or not?
Yeah, where does it fade? Yeah. Okay, I think I might already be a little over time, but thank you guys very much.
You're right, it was a different talk.